In the northern land of Scotland, where the wind moves across green hills and the sound of distant waves seems to whisper secrets of the cosmos, a child was born who would one day decode the invisible language of nature itself. It was June 13, 1831, in Edinburgh, when James Clerk Maxwell entered the world, not as a prodigy born to privilege or fame, but as a quiet observer destined to uncover the hidden unity of all physical laws. His birthplace, full of old stones, rolling meadows, and the hum of nature's mystery, shaped the earliest impressions that would one day fuel his scientific imagination. From the very beginning, Maxwell was different. As a child, he didn't play as most others did. While others ran through the fields chasing sunlight, James would stop to trace the pattern of ripples in a pond or the symmetry of light reflecting on glass. He saw things not only as they appeared but as they truly were, guided by some deep curiosity to find the reason behind every phenomenon. His mother, Frances Maxwell, was the one who first noticed this boundless curiosity. She encouraged him to look into everything carefully, a simple sentence that would become the philosophy of his entire life. She was gentle and educated, deeply devoted to nurturing his mind, and she recognized early that her son's questions were not ordinary. Young James would ask questions endlessly about the shape of clouds, the colors of rainbows, why the stars twinkled differently, why objects moved the way they did. For him the world was not a place of random beauty, but a vast puzzle waiting to be solved. His mother would often sit beside him as he drew shapes on the floor or constructed simple experiments from string, glass, and candlelight, trying to understand how light could bend and split into colors. But fate can be cruel to gifted souls. When James was just 8 years old, his mother passed away after a painful illness. Her death struck deeply, leaving an emotional emptiness that would never truly fade. Yet, her influence endured. Her lessons of curiosity and patience became the moral compass that guided James's mind. After his mother's death, James's father, John Clerk Maxwell, took responsibility for his education. John was a landowner and engineer, a man of solid character, practical in his thinking yet supportive of his son's strange fascinations. The two shared a special bond, father and son wandering through the fields of their estate, Glenlair, where James would study patterns in the soil, watch light dancing across water, and sketch geometrical figures in the dirt. Glenlair became his first laboratory, nature his teacher, and silence his companion. But in the small schools of Scotland, Maxwell's genius was often misunderstood. His teachers thought him strange, sometimes even slow, because his curiosity made him think too deeply, his answers too elaborate for simple questions. He was teased by classmates who didn't understand why he drew geometric patterns or carried notebooks filled with diagrams of circles and lines. Yet, behind that shy demeanor was a mind far ahead of its time. Every ridicule, every doubt, every misunderstanding only pushed him deeper into his world of thought. A private universe where ideas moved like constellations waiting to be mapped. At the age of 10, his father sent him to the Edinburgh Academy, hoping to give him a proper education. It was there that the young boy began to find the structure that his wild curiosity needed. Still, even at school, James was not the kind of student who memorized facts or obeyed conventional teaching. He preferred to discover knowledge for himself. While others repeated what was written in textbooks, Maxwell questioned the reason behind every principle. Why did light travel in straight lines? Why did magnetic fields curve? Why did soap bubbles form perfect spheres? These weren't just questions for him, they were doorways into the fabric of reality. In his teenage years, the world of mathematics began to reveal itself as the perfect tool to express what his imagination already sensed. Numbers and symbols became his artistic language, a way to capture the invisible laws of the universe. He found beauty in equations, not as cold abstractions but as expressions of order and harmony. The more he studied, the more he realized that geometry, algebra, and physics were not separate disciplines, but parts of one great tapestry that connected everything. At just 14, Maxwell presented his first scientific paper to the Royal Society of Edinburgh, an astonishing achievement for a boy still in school. The paper, titled On the Description of Oval Curves, explored how complex geometrical figures could be represented through mathematical equations. It was not just an exercise in mathematics, it was a glimpse into his future mind, the same mind that would later unite electricity, magnetism, and light. He was already thinking beyond the visible, beyond the conventional boundaries of knowledge. When the audience of seasoned scientists realized that this intricate paper had been written by a schoolboy, they were stunned. It was a moment of revelation. The quiet boy from Edinburgh was no ordinary student, he was a mind destined to shape physics itself. Maxwell's curiosity extended to everything he encountered. He experimented with mirrors and light, studied colors and shadows, and even analyzed how honeycomb structures formed. To him, science wasn't just a study, it was a living, breathing conversation with the natural world. He once wrote in his diary that, "It is the glory of geometry that from so small beginnings, it can lead to such great things." He could look at a soap bubble and see the laws of pressure and curvature. He could study a ray of light and imagine the electromagnetic vibrations behind it. At home, his father encouraged his experiments, turning their estate into a laboratory of discovery. He built small contraptions to test the elasticity of materials, studied the reflection of light using water surfaces, and even investigated how colors mixed and changed when combined, an early precursor to his later studies in color vision. The boy who once asked questions about rainbows was now exploring the mathematics behind them. His environment also nurtured his creativity. The Scottish countryside, with its mist, its changing skies, and its endless play of light, became a living textbook for Maxwell. He watched how sunlight scattered through rain, how shadows shifted at different times of day, and how reflections danced on the surface of rivers. Nature, for him, was not random, it followed laws that could be written, measured, and understood. This harmony between observation and imagination became the essence of Maxwell's thinking. Even his faith and sense of wonder added depth to his science. He believed that understanding the universe was, in a way, understanding the language of creation. Unlike many scientists of his time who separated faith and science, Maxwell saw them as partners, both seeking truth in different forms. His humility kept him grounded even as his intellect soared. He once wrote, "I believe the glory of God lies in the unity of His creation, and science is but the discovery of His work." As Maxwell grew older, his early education began to crystallize into purpose. The questions that once seemed like innocent childhood curiosities were now transforming into rigorous scientific pursuits. He began to see connections between mechanical motion and electromagnetic behavior, between waves in water and waves in light. The mathematical structures he had once used to describe ovals now helped him describe the oscillations of electric and magnetic fields. It was as though his entire youth had been preparing him for a single realization: that nature itself was written in the elegant script of mathematics. Those who met Maxwell in person often described him as shy, soft-spoken, but with an intensity that emerged when he spoke about science. His classmates, once puzzled by his obsessions, began to admire him for his brilliance. He was not a showman like Faraday nor a philosopher like Newton. He was a thinker whose ideas spoke louder than his words. His mind moved with quiet precision, his imagination guided by logic, his curiosity fueled by awe. One of the most touching aspects of Maxwell's youth was his approach to learning, not through memorization or ambition, but through pure love of discovery. He could spend hours studying how light reflected through a crystal, not because anyone told him to, but because he felt a need to understand it. He believed knowledge should not just be learned but experienced, and that the joy of uncovering truth was a reward in itself. This passion for self-driven discovery became the foundation for his later breakthroughs in electromagnetism. His fascination with color was another defining feature of his early years. Maxwell conducted experiments with spinning color wheels to determine how the human eye perceives color combinations. These experiments led him to formulate mathematical models for color vision, laying the groundwork for modern color photography. Even in this, his youthful curiosity shone through. He didn't just want to know what color was, he wanted to know why the human mind saw it that way. The same curiosity that once made him stare into rainbows now turned into scientific understanding of light. In the evenings, when the world around him grew quiet, Maxwell would often read poetry and philosophy. He believed science and art were not opposites, but reflections of the same creative spirit. He admired the works of poets like Wordsworth and thinkers like Bacon and Newton, finding in their words the same search for order and meaning that guided his science. This blend of imagination and intellect gave his work a rare poetic beauty. His equations, though technical, carried a rhythm that echoed harmony rather than chaos. His intellectual brilliance did not make him proud, instead, it made him more humble. Maxwell once said that, to comprehend nature's laws is to see only a glimpse of something infinite. For him, every discovery led to deeper mystery. His childhood curiosity never faded. Even as he mastered the most complex mathematics, he retained that same innocent wonder he had as a boy in Glenlair. The world around him was changing fast. The 19th century was a time of industrial growth, technological progress, and scientific revolutions. Steam engines powered cities, electricity was becoming known, and telegraphs were beginning to connect continents. Yet in this age of invention, there remained vast mysteries about how these forces worked. Young Maxwell sensed that behind these advancements lay deeper laws that could explain not just how electricity or magnetism behaved, but why they existed in harmony. His childhood curiosity had matured into a mission to find unity in the forces that govern nature. He carried into adulthood the same qualities that defined his youth: patience, humility, and relentless curiosity. It was this combination that would allow him, in later years, to see the invisible connections others missed. Just as he once studied light in a glass of water, he would later study light as a wave traveling through electromagnetic fields. Just as he once traced geometric patterns in the dirt, he would later write equations that mapped the patterns of the universe itself. The early life of James Clerk Maxwell was not a story of instant recognition or fame. It was the story of a mind quietly preparing to change humanity's understanding of reality. Every question he asked, every sketch he made, every reflection he observed was a step toward that future revelation. His childhood was the seed of genius, a gentle beginning that would grow into the greatest unification in physics before Einstein. And though the world did not yet know it, the boy who once stared into rainbows and patterns would one day connect the very forces that shape existence: light, electricity, and magnetism, revealing that the universe itself speaks one language, and he was the first to write it down. As James Clerk Maxwell grew into his later teenage years, the glow of curiosity that had guided his childhood did not dim. Instead, it deepened into something more disciplined, more visionary. The boy who once traced circles in the dirt of Glenlair now filled pages with equations that captured the invisible geometries of nature. He had learned that curiosity alone could ignite discovery, but understanding demanded structure. Every observation had to be measured, every pattern expressed in the clarity of mathematics. What began as wonder was becoming mastery. At the Edinburgh Academy, Maxwell's brilliance had already begun to unsettle his teachers. They could not understand how a student could see meaning in every simple experiment, how he could turn a problem of geometry into a meditation on symmetry and design. He often asked questions that went beyond the curriculum, questions no teacher could answer. Yet his teachers soon realized that their quiet pupil possessed not just intelligence, but an almost mystical insight into how the world worked. It was as if he could see through appearances into the inner harmony of things. His notebooks from this period were filled with diagrams that revealed the precision of his thinking. Every curve, every symbol seemed to carry intention. He was not merely solving mathematical problems, he was describing how the universe thinks. To him, mathematics was not a tool but a language older than words, spoken by nature itself. This conviction would later allow him to express the unity of electricity, magnetism, and light in 4 concise equations, but the seed of that power was planted here in his youth, when curiosity met form. Outside of school, Maxwell spent hours exploring the physical world. He built simple instruments, rotating mirrors, glass prisms, pendulums, and used them to study reflection, motion, and light. He wanted not only to observe phenomena, but to see through them. When he spun a color wheel and watched different pigments blend into white, he sensed that color was not merely art, but a phenomenon governed by numbers and waves. When he saw ripples move across water, he imagined how similar vibrations might travel through space itself. Every observation was a metaphor for a deeper law. By the time Maxwell entered the University of Edinburgh, he was already recognized as an extraordinary student. Yet he remained modest, almost hesitant about his own talent. His classmates often described him as polite, deeply thoughtful, sometimes lost in contemplation. He would listen more than he spoke, and when he did speak, his words carried the quiet conviction of someone who had thought deeply before uttering a single sentence. He believed knowledge should be pursued for its own sake, not for fame or reward. His joy was in discovery itself. At the university, he studied mathematics, philosophy, and natural philosophy, a blend that shaped his intellectual foundation. His professors quickly realized that he was not a typical student. While others were content to memorize equations, Maxwell asked what those equations meant, what story they told about nature's design. He challenged assumptions, not out of rebellion, but out of an unshakable need to understand. When others saw separate fields, geometry, optics, mechanics, Maxwell saw a hidden unity, an underlying pulse connecting all things. His experiments in optics grew more sophisticated. Using spinning discs painted with different colors, he tested how the human eye perceived combinations of red, green, and blue. From these observations, he deduced that all colors could be created by mixing those 3 primary hues. Years later, this insight would lead directly to the world's first color photograph, a ribbon of tartan captured through filters representing red, green, and blue light. What had begun as the playful curiosity of a boy staring into rainbows became the foundation of color science. During these formative years, Maxwell also developed a deep appreciation for the philosophy of science. He read the works of Descartes, Newton, and Faraday, absorbing their ideas but also questioning them. He believed that science should not only describe how things happen, but explain why they happen. This belief guided him toward the notion that the physical world is governed by relationships, fields and forces that bind matter together. Even as a student, he began sketching mental models of invisible structures that might carry electric and magnetic influence through space. He did not yet have the equations, but his imagination had already glimpsed the form of his later discoveries. One of Maxwell's remarkable qualities was his combination of intuition and precision. Many scientists of his time were either experimenters or theorists. Few could do both with equal skill. Maxwell, however, could move effortlessly between the laboratory and the chalkboard. He could imagine a phenomenon, test it with his own hands, and express it with mathematics so elegant that it seemed inevitable. His brain was like a bridge between 2 worlds, the physical and the abstract. At the age of 19, he transferred to the University of Cambridge, the intellectual heart of the British scientific tradition. It was here that his raw genius began to mature into systematic brilliance. Cambridge in the mid-19th century was a world alive with new ideas. Mechanics, thermodynamics, and optics were being transformed by discoveries across Europe. Yet even in this environment of great minds, Maxwell stood apart. His tutors quickly realized that his capacity for abstraction was extraordinary. He could grasp the essence of complex mathematical structures and see connections invisible to others. But what made Maxwell unique was his temperament. He was never arrogant, never boastful, Despite his intellectual superiority, he treated everyone with kindness and curiosity. He often helped classmates who struggled with mathematics, explaining concepts with patience and clarity. To him, teaching was another form of discovery. He once said that if you truly understand something, you should be able to explain it simply. That belief stayed with him throughout his life, even when his own work became the foundation for modern physics. Cambridge also refined his sense of beauty in scientific expression. He admired Newton's Principia, not just for its results but for its elegance. The way complex truths could be expressed through simple mathematical forms. Maxwell sought the same grace in his own work. When he later formulated the equations that bear his name, he wrote them not merely as calculations but as poetry, lines of mathematics that sing of unity and order. Outside his formal studies, Maxwell found joy in the natural world. He loved horseback riding, long walks, and the play of sunlight across landscapes. Even in leisure, his mind remained curious. He observed how light shifted at dawn and dusk, how the air shimmered after rain, how the wind sculpted patterns on the grass. Every detail seemed to whisper a secret about the forces at work beneath the surface. He once told a friend that the beauty of the world was the greatest invitation to study it. During his time at Cambridge, Maxwell began exploring ideas about mechanical analogies, ways to represent invisible forces through tangible systems. He imagined fields as if they were fluids, lines of force as streams in motion. These analogies helped him picture abstract relationships in physical form. Although some of these models were later replaced by more advanced theories, they served as essential steps in his journey toward understanding electromagnetism. They reflected his belief that imagination is not the opposite of logic but its partner. As the years passed, Maxwell's reputation grew. Professors admired his insight, peers respected his intellect, yet he remained modest, almost unaware of his own rising status. He never sought the spotlight, preferring the quiet company of ideas. When he graduated with high honors, his teachers knew they were witnessing the beginning of a legacy that would echo for centuries. Returning to Scotland after Cambridge, Maxwell accepted a teaching position at Marischal College in Aberdeen. There, he continued his experiments in color and geometry while mentoring young students. His lectures were known for their clarity and enthusiasm. He brought science to life, using everyday examples to explain complex concepts. Students recalled his passion and warmth. He was not merely a teacher of facts but a guide to wonder. In these years, Maxwell's early curiosity found expression in many forms. He studied Saturn's rings, developing mathematical proofs to show that the rings could not be solid or liquid, but must consist of countless small particles. His conclusion was later confirmed by space probes more than a century afterward, a testament to the accuracy of his reasoning. Even here, we see the same pattern: a mind that could take simple observation, apply pure thought, and reveal truths far ahead of its time. What truly defined Maxwell's early brilliance was his sense of unity. He saw no boundaries between disciplines. Mathematics, physics, philosophy, even art were all parts of one grand search for truth. He once wrote, "In the pursuit of science, we are seeking not only knowledge, but the beauty that comes with understanding." That conviction guided him to treat every problem as part of a larger whole. By his late 20s, Maxwell had already contributed to several fields: optics, thermodynamics, mechanics. But the deepest current in his thought was still forming. All his childhood fascinations, the patterns of light, the geometry of motion, the play of color, were converging toward a single vision that the universe was bound together by invisible relationships, fields that carried energy and information through space. He did not yet have the mathematical form to describe them completely, but the idea was alive within him, waiting for the moment when inspiration and experience would merge. The story of his youth, then, is not just a tale of talent, it is a chronicle of persistence. Maxwell's path was not paved with applause. Many of his early papers were met with confusion, even indifference. But he never stopped asking questions, never stopped believing that every mystery held an answer waiting to be found. His curiosity was his compass, and it guided him unerringly toward the heart of nature's secrets. In the quiet of Glenlair, he often returned to his childhood home, walking the fields where his first questions had been born. There, amid the same hills and rivers, he reflected on how far he had come, and how much further the journey would go. He felt gratitude for his father's support, for the memory of his mother's encouragement, and for the enduring power of curiosity that had shaped his entire being. Those who knew him in those years saw a man whose mind was vast yet whose spirit was humble. He treated science not as conquest but as conversation with creation. Every equation, every experiment was a way of listening to what the universe was saying. He once remarked that the scientist's duty is to think God's thoughts after him, not in arrogance, but in reverence for the laws that sustain all things. The young Maxwell story is more than biography, it is a testament to how wonder becomes wisdom. His early years reveal that genius is not a gift of knowledge but a gift of perception, the ability to see meaning where others see nothing. From the shimmering rainbows of his childhood to the precise mathematics of his youth, every moment was a step toward unveiling the invisible. In time, these early seeds would bloom into one of humanity's greatest intellectual achievements, the unification of light, electricity, and magnetism. But that revolution began not in the laboratory, not in a burst of fame, but in the quiet curiosity of a child who refused to stop asking why. To understand Maxwell's later triumphs, one must first see this, the boy who saw geometry in raindrops, harmony in light, and purpose in curiosity. His youth was the prelude to a symphony that would one day resound through the halls of science, shaping everything from radio waves to quantum theory. When the world finally recognized the magnitude of his genius, long after his death, it became clear that the roots of that genius lay in these early years of patient exploration. The spark that ignited his mind at Glenlair became the flame that illuminated modern physics. He showed that true brilliance does not come from knowing everything, but from never ceasing to ask, to seek, to imagine. And so, as the sun set over the Scottish fields where a young James once traced the patterns of nature, it marked not an end but a beginning. The questions born in that gentle landscape would echo across centuries, carried by every beam of light, every wave of electricity, every magnetic field that hums through the universe. James Clerk Maxwell, the curious child, the humble scholar, the genius who listened to the whispers of creation, began his journey with a single thought, that there is order behind mystery, beauty behind mathematics, and unity behind all things. The early light of his curiosity still shines, guiding generations toward the same horizon he once gazed upon, a horizon where knowledge and wonder meet. The story of how James Clerk Maxwell gave birth to one of the most powerful ideas in all of science begins not in the flash of a laboratory discovery, but in the quiet persistence of thought. It is the story of a man who took invisible forces, electricity and magnetism, and revealed that they were not separate, chaotic entities, but two faces of the same universal truth. In uniting them, Maxwell would do for electromagnetism what Newton had done for motion and gravity, find order in the unseen. Yet this journey began not with fame or fortune, but with curiosity and a desire to see the unity behind nature's apparent complexity. In the mid-19th century, the scientific world was alive with discovery, but filled with confusion. Experiments had revealed strange behaviors of electric and magnetic forces, but no one could explain their underlying connection. Electricity could shock, magnetism could attract or repel, and both could move through materials in mysterious ways, yet these phenomena seemed to exist in separate worlds. Scientists like Charles, Augustin de Coulomb, André-Marie Ampère, and Michael Faraday had uncovered individual pieces of the puzzle. Coulomb had measured the force between electric charges. Ampère had shown that electric currents could create magnetic fields, and Faraday had demonstrated that a changing magnetic field could produce electric current. But the grand picture, the underlying unity that tied these facts together, remained hidden. Maxwell, with his deep mathematical mind and poetic imagination, sensed that these were not isolated curiosities. He believed that nature's laws must be connected by a deeper harmony, a symmetry that could be written in the precise language of mathematics. To him, Faraday's lines of force, those invisible curves through which electric and magnetic effects were imagined to flow, were not mere sketches or metaphors. They were the very structure of reality. Yet Faraday, though one of the greatest experimentalists in history, lacked the mathematics to express his discoveries fully. Maxwell admired him deeply, and where Faraday had seen in pictures, Maxwell began to see in equations. When Maxwell first turned his attention to electromagnetism in the early 1850s, he was still a young scholar in his 20s. He had already studied color and optics, and his mathematical ability had drawn attention from leading scientists. But now, he was fascinated by the mysterious dance between electricity and magnetism. The challenge was immense. There was no single theory to build upon, only scattered laws and experimental results, each describing one small part of a vast invisible mechanism. Yet Maxwell approached this chaos not as a problem, but as a melody waiting to be harmonized. He began by revisiting Faraday's experiments and translating them into the rigorous structure of mathematics. Faraday had described electric and magnetic forces as fields, regions of space filled with influence, capable of acting at a distance. Maxwell saw in this concept something revolutionary. Until then, scientists had often imagined that forces acted instantly across empty space, as Newton's gravity was believed to do. But Faraday's idea suggested that the space itself, filled with invisible lines of force, carried the influence. Maxwell's mathematical insight gave this vision substance. He began to describe how these fields might interact, how a changing electric field could give rise to a magnetic one, and how, in turn, a changing magnetic field could create an electric one. At first, he worked in analogies. He imagined space filled with tiny rotating vortices, like microscopic whirlpools, carrying the magnetic influence, while electric charges were imagined as particles embedded in this invisible medium. These mechanical analogies may seem strange today, but they were the stepping stones to something far greater. By creating these models, Maxwell could translate the intuitive ideas of motion, stress, and elasticity, concepts from mechanics, into the abstract realm of electromagnetism. Slowly, the mathematics began to reveal a pattern. Through years of careful reasoning, Maxwell combined the known laws of electricity and magnetism into a single framework. He started with Coulomb's law, describing the electric force between charges, and added Ampere's law, showing how electric currents create magnetic fields. He included Faraday's law of induction, showing how changing magnetic fields produce electric currents. But when he looked closer, he saw that these laws, as they stood, were incomplete. There was something missing, a small but crucial piece that prevented them from being truly symmetrical. In his equations, Maxwell noticed that a changing electric field seemed to play no role in generating magnetism, even though a changing magnetic field clearly generated electricity. Nature, he thought, could not be so unbalanced. He began to suspect that there must be an additional term, a hidden current, so to speak, that would restore the symmetry. He called this new quantity the displacement current. This idea was revolutionary. It suggested that even in empty space, where no physical charge moves, a changing electric field could create a magnetic effect. This was the missing link that united electricity and magnetism into one grand theory. With the displacement current included, Maxwell's equations became complete, a perfect mathematical structure describing how electric and magnetic fields are intertwined. To test the power of his equations, Maxwell examined what would happen if an electric field and a magnetic field continually generated each other in space. The mathematics told him something astonishing, such a self-sustaining disturbance would travel through space as a wave, moving at a specific speed. When he calculated that speed using known values for electrical and magnetic forces, he found that it matched exactly the measured speed of light. It was a moment of breathtaking revelation. Light, that ancient mystery studied by philosophers for centuries, was not something separate or mysterious at all. It was an electromagnetic wave born from the interplay of electricity and magnetism. Maxwell's realization connected optics, electricity, and magnetism into a single theory of nature. What Newton had done for gravity, Maxwell had now done for electromagnetism. He wrote in his notes, with quiet wonder, that light and electromagnetic disturbances are of the same nature. In that one insight, he transformed physics forever. For the first time, light was understood not as a special phenomenon, but as part of a larger spectrum of waves. Maxwell predicted that other forms of electromagnetic radiation must exist, waves longer and shorter than visible light, traveling invisibly through space. Decades later, these would be discovered as radio waves, X-rays, and microwaves, all the technologies that now define the modern world. But in Maxwell's time, his theory was not easily accepted. His contemporaries struggled to grasp the meaning of his abstract equations. They admired his mathematics, but could not fully imagine the invisible waves he described. The mechanical analogies that had helped him reach his conclusions were dismissed by some as speculative. Yet Maxwell knew that his model was not literal but conceptual, a way of thinking that allowed mathematics to express truths beyond direct observation. He once said that it mattered little whether the medium he imagined really existed. What mattered was that the equations captured the behavior of the world accurately. The publication of his landmark paper on physical lines of force 1861-62 marked the first full presentation of his electromagnetic theory. In this work, he outlined how electric and magnetic fields interacted and how energy was stored and transmitted in space. He envisioned the electromagnetic field as a physical entity capable of carrying energy and momentum. This concept, that energy could exist in the field itself, even in the absence of matter, was another profound leap that would later shape Einstein's relativity and the birth of quantum theory. Maxwell's achievement, however, was not simply in discovering a set of equations. It was in recognizing their unity, their ability to describe seemingly different phenomena through a single framework. His 4 equations could describe the behavior of every electrical circuit, every magnetic interaction, every ray of light. They contained within them the principles behind radio communication, radar, electric motors, and the transmission of energy across space. Yet Maxwell himself lived before most of these technologies existed. He could only imagine what might one day be possible. His approach combined the rigor of mathematics with the intuition of imagination. To Maxwell, equations were not cold abstractions, but living expressions of nature's rhythm. Each symbol carried meaning, each term represented a physical relationship. He saw beauty in their symmetry and elegance. He once said, "The true logic of the world is the calculus of relations." In his equations, the world was no longer a collection of separate forces, but a single, self-consistent field of energy and motion. As he refined his work, Maxwell often reflected on the philosophical meaning of his discoveries. He wondered what it meant for light to be a wave in an invisible medium. What kind of substance could fill all space, and yet allow such motion? At the time, scientists still believed in the existence of the luminiferous ether, a mysterious medium thought necessary for light to propagate. Maxwell's theory fit neatly into that framework, but his equations themselves did not depend on the ether. In fact, when Einstein later developed the theory of relativity, he would show that no such medium was needed, that light could move through empty space because space itself carried the electromagnetic field. Maxwell's mathematics had already made this possible. The birth of Maxwell's equations was not just the union of electricity and magnetism. It was the birth of the modern concept of the field, an entity that could exist independently of matter, filling all of space, transmitting forces and energy. This idea would become the foundation for all 20th century physics, From Einstein's relativity to quantum field theory, Maxwell had unknowingly given scientists a new way to think about reality, not as a set of objects interacting at a distance, but as a continuous web of fields connecting everything. In his own time, though, Maxwell was more modest. He continued his teaching and research, refining his ideas and explaining them with patience. He often worked late into the night, surrounded by notebooks filled with elegant lines of algebra and vector calculus. Those who visited his study said he would pause, stare into space, and then suddenly smile, as if he were listening to a conversation between nature and mathematics. His wife, Catherine, supported him tirelessly, organizing his papers and encouraging him through moments of exhaustion and doubt. She knew, perhaps better than anyone, that her husband was reshaping the way humanity understood the universe. As the 1860s progressed, Maxwell gathered his ideas into a monumental book, a treatise on electricity and magnetism published in 1873. Within its pages lay the full form of his theory, the 4 equations that now bear his name. Few could immediately grasp their depth, but the seeds were planted. In those pages, Maxwell had written the language that would one day power cities, transmit voices across continents, and send signals through the vacuum of space. To him, it was never about glory. He saw himself not as a conqueror of nature, but as an interpreter of its harmony. He once wrote, "We may find ourselves listening to the whispers of creation, not in words, but in numbers." His equations were those whispers, transcribed into the universal script of mathematics. Even before experimental confirmation, Maxwell trusted his results because they carried the mark of beauty and coherence. To him, the symmetry of his equations was a sign of truth, a reflection of the underlying unity of nature, and indeed time would vindicate him. In 1888, a decade after his death, Heinrich Hertz would generate and detect radio waves, proving experimentally what Maxwell had predicted purely through theory. That moment confirmed his vision. Electricity and magnetism were 2 aspects of the same fundamental phenomenon. The unity Maxwell found between these forces was more than scientific, it was philosophical. It showed that nature's apparent diversity hides an underlying simplicity, that all things are connected through invisible relationships. In revealing this, Maxwell did not just explain how the universe works, he changed how humanity perceives it. The modern world, from every electric light to every wireless signal, hums with the echoes of his discovery. In those quiet Scottish nights where he once gazed at the stars, Maxwell had dreamed of harmony. Through his equations, he gave that harmony form. The dance of electricity and magnetism that powers the modern age is the same music he first heard in the patterns of nature. His genius was not only in seeing the unity of forces, but in feeling it, in knowing that beauty, truth, and mathematics all speak the same universal language. The world did not immediately awaken to what Maxwell had done. His treatise on electricity and magnetism sat quietly on the shelves of university libraries, its dense mathematics understood by only a handful of readers. But inside those pages lay a vision that would one day electrify civilization. When Maxwell died in 1879, only a small circle of physicists realized that a revolution had just been written in symbols. Yet revolutions sometimes unfold slowly, their ripples spreading outward through generations until the world finally feels their power. The first ripples came from a young German physicist, Heinrich Hertz. In the late 1880s, Hertz built upon Maxwell's mathematics with ingenious experiments. He arranged sparks, wires, and oscillating circuits in a darkened laboratory and asked a simple question: could these equations truly describe waves moving through the air, invisible to the eye yet real? One night, the faint crackle of a secondary spark answered him. A tiny blue flash jumped across a gap a few feet away. Maxwell's prediction had come alive. Hertz had produced electromagnetic waves, radio waves without wires, purely through the oscillation of electric and magnetic fields. In that moment, the invisible web Maxwell had imagined became visible in its effects. Hertz measured the wavelength, the reflection, and the refraction of these waves, confirming every one of Maxwell's theoretical laws. he proved that light itself was simply a higher, frequency version of the same phenomenon. Electricity and magnetism were indeed one. The equations were not just mathematics, they were nature's grammar. Hertz's work sparked a chain of invention. Scientists such as Guglielmo Marconi, Nikola Tesla, and Oliver Lodge began exploring how to control these waves, how to make them carry signals across oceans and continents. The birth of radio, the first voice sent through empty space, was a direct descendant of Maxwell's unification. From the quiet of his Scottish study, the equations had traveled into every home, into every corner of the modern world. Telegraphs without wires, ships guided by invisible beacons, entire cities connected by unseen vibrations, all of it grew from the same mathematical seed. But Maxwell's legacy did not stop with communication. His concept of the electromagnetic field transformed physics itself. Before him, the universe had been thought of as a stage filled with discrete particles acting upon one another through direct forces. After Maxwell, reality became a continuous fabric of fields, each point in space carrying energy and momentum. Matter was no longer king, the field was. This shift in perspective laid the foundation upon which Albert Einstein would later build his theory of relativity. When Einstein studied Maxwell's equations as a student, he was struck by their perfect symmetry. They described light moving at a constant speed, independent of any observer. Yet Newtonian mechanics, with its notion of absolute space and time, could not accommodate this. The tension between these two worldviews gnawed at Einstein until in 1905 he resolved it with the special theory of relativity. Einstein would later write that the theory of relativity owed its origin to Maxwell's electromagnetic field theory. Without Maxwell, there would have been no Einsteinian revolution. The constancy of the speed of light, an assumption built into Maxwell's equations, became the cornerstone of modern physics. In uniting electricity and magnetism, Maxwell had also bound together space and time. The consequences were cosmic. Even the technologies of the 20th and 21st centuries, power generation, electric motors, transformers, radar, television, computers, satellites, are but practical expressions of Maxwell's ideas. Every current running through a wire, every electromagnetic signal beamed across the sky, follows the laws he discovered. In every electric hum of civilization, the spirit of his equations resonates. It is a whisper that connects the light bulb in a home to the auroras in the polar sky, the data in a phone to the energy of the stars. Yet for all its success, Maxwell's theory also opened new mysteries. His continuous waves seemed at odds with the emerging discoveries of the atomic world. If light was a wave, how could it sometimes behave like a particle? The next century would grapple with that paradox, giving birth to quantum mechanics. And even there, Maxwell's shadow would fall. The quantum field theories that govern modern physics, electrodynamics, chromodynamics, and beyond, are extensions of his concept of the field. The entire language of modern physics is, in essence, Maxwellian. In the decades after his death, universities slowly began to teach his work more widely. Students pored over his treatise, guided by the simplified notation introduced by Oliver Heaviside, who condensed Maxwell's lengthy 20 equations into the 4 elegant expressions we use today. These 4 equations became the Rosetta Stone of electromagnetism, concise enough to fit on a page yet vast enough to explain the behavior of the cosmos. Heaviside, like a sculptor uncovering a hidden form, revealed the clean structure beneath Maxwell's original complexity, making it accessible to engineers and physicists alike. Through this transformation, Maxwell's vision became the operational heart of technology. Meanwhile, in the practical world, the Industrial Revolution was shifting gears. Electricity was beginning to replace steam as the lifeblood of modern infrastructure. Power stations, electric lighting, and telecommunication systems all relied on principles derived from Maxwell's equations. Engineers designing alternators and transformers unknowingly echoed his mathematics in every coil and circuit. The link between theory and application became so seamless that one could hardly imagine a world without it. But beyond the laboratories and factories, Maxwell's unification carried a philosophical resonance. It spoke of coherence in the universe, of an underlying simplicity beneath complexity. It suggested that the same laws that governed a laboratory experiment also governed the stars. This unity appealed not only to scientists but to thinkers, poets, and philosophers who saw in it a metaphor for the harmony of creation. Maxwell himself, a man of both science and faith, often reflected on the wonder of such coherence. To him, the mathematical order of the universe was not cold or mechanical. It was a reflection of a deeper beauty, something almost sacred. As the 20th century advanced, experimental confirmation of Maxwell's vision multiplied. The discovery of the electromagnetic spectrum unfolded like a revelation. Radio waves, microwaves, infrared visible light, ultraviolet, X-rays, gamma rays, all manifestations of the same fundamental field. Each new window opened by technology merely expanded the melody he had composed. Humanity learned to tune the invisible strings of the cosmos, transforming Maxwell's equations into symphonies of sound and image. The entire electromagnetic spectrum became our instrument for exploration, from radar mapping the Earth to telescopes peering across billions of light years. Every photograph of a distant galaxy, every broadcast, every Wi-Fi signal is an unspoken tribute to his insight. Still, the path from discovery to recognition was gradual. Only long after his death did Maxwell's name rise beside Newton's and Einstein's in the pantheon of physics. Historians began to see that he had done more than unify two forces. He had introduced an entirely new way of conceiving nature. Where Newton saw forces acting between particles, Maxwell saw continuous fields connecting everything. This change in vision turned out to be one of the greatest conceptual shifts in human thought. In classrooms today, students learn Maxwell's equations as formulas to be memorized, yet behind those symbols lies a story of imagination, perseverance, and humility. He did not chase wealth or fame, he chased understanding. When his health declined, he continued working, concerned not about his own name, but about ensuring his equations were clear enough for future generations to use. The young scholars who visited him near the end of his life often described a quiet gentleness, a man who could turn from complex mathematics to quote poetry, who could speak of the beauty of a sunset with the same wonder he found in the logic of calculus. After his passing, his colleagues at Cambridge erected memorials and named laboratories in his honor. The Cavendish Laboratory, which he helped design, would later become the birthplace of the atomic nucleus, the electron, and the structure of DNA. It was as if Maxwell's spirit continued to guide every major discovery that took place there. The network of knowledge he had woven, connecting light, electricity, and magnetism, had expanded to connect all of physics itself. Even now, more than a century later, scientists return to Maxwell for inspiration. Spacecraft navigating through interplanetary fields, quantum computers manipulating electromagnetic interactions, medical imaging revealing the hidden structures of the human body, all rely on his principles. The satellites that beam signals to Earth trace their ancestry back to his four equations. In every glowing screen, every digital transmission, his vision breathes, and yet there remains a poetic irony in his legacy. The man who connected the forces of the universe died before he could see the full light of his own creation. He lived in a world lit by candles, unaware that his equations would one day illuminate entire continents. He could not have imagined skyscrapers glittering with electric light or humans communicating across oceans through invisible waves. But he had faith that understanding nature's harmony would yield wonders beyond imagination. History proved him right. As documentaries and historians recount his life today, the image that emerges is not only of a mathematician but of a visionary philosopher. Someone who saw unity where others saw division, order where others saw chaos. His legacy reminds us that progress is not only born from invention but from imagination. The equations he wrote are, in essence, poetry written in mathematics, a language that still speaks to every scientist who seeks to uncover the hidden symmetries of the world. In the grand timeline of science, Maxwell stands as a bridge between the mechanical universe of Newton and the relativistic and quantum universe of the 20th century. His work is the turning point where the old world ended and the new began. Through his mind, humanity stepped from the age of classical forces into the era of fields and waves, and through those fields and waves came the technologies that shape modern civilization. Whenever a lightning bolt flashes, whenever a compass needle swings, whenever light glints off a mirror, or an antenna sends a signal into space, the invisible choreography of Maxwell's equations unfolds. They operate silently, endlessly, indifferent to time or place, linking past and present. The pulse of modern life, measured in gigahertz and megawatts, beats to the rhythm he first discerned. The genius who connected light, electricity, and magnetism gave humanity more than scientific laws. He gave us a way to see the universe as a single, harmonious whole, a cosmos woven together by fields of energy and governed by beauty. His story reminds us that the greatest discoveries are not just about what we observe, but about how we choose to imagine the unseen. Maxwell imagined the invisible, and in doing so, illuminated everything. As the final credits of his Untold story would roll in a film, one could picture him standing in the dim light of his laboratory, chalk in hand, gazing at the symbols on a blackboard that only he fully understood. Outside, the world was dark, unaware that the equations glowing faintly in candlelight would one day light the world itself. The equations of James Clerk Maxwell, simple, elegant, eternal, remain humanity's most powerful bridge between thought and reality, between the mystery of light and the pulse of electricity, between imagination and truth. When James Clerk Maxwell died in 1879, few could have imagined that his equations would become the seed of the entire modern scientific world. His funeral was quiet, attended by family, students, and a handful of scientists who truly understood what he had accomplished. Yet in that silence, the universe had already changed. The invisible forces that Maxwell had united, electricity, magnetism, and light, were only the beginning. His mathematics had set in motion a chain of discovery that would ripple across generations, unlocking mysteries far beyond anything he could have dreamed. In the closing decades of the 19th century, the air of science was heavy with both triumph and uncertainty. The great mechanical laws of Newton still reigned supreme, explaining the motions of planets and machines alike. But under the surface, anomalies were beginning to appear, subtle cracks in the classical worldview. Scientists could not yet see it clearly, but the universe was preparing to reveal a deeper layer of reality, one that would rewrite the foundations of physics. At the heart of that transformation stood Maxwell's vision of the electromagnetic field. The first to pick up the torch after Maxwell's passing were the experimentalists. In the 1890s, a German physicist named Heinrich Hertz had already proven the existence of electromagnetic waves, confirming Maxwell's predictions beyond any doubt. But Hertz had done more than verify an equation. He had opened a window into a new world of invisible waves, each vibrating with its own frequency and carrying energy across the emptiness of space. Scientists began to ask if these waves existed everywhere, what else might they reveal? What secrets did the electromagnetic field still hold? The answer came unexpectedly from a darkened laboratory in Cambridge, where a young physicist named J.J. Thomson was studying electrical discharges in vacuum tubes. It was 1897 when Thomson made his stunning announcement. Electricity was not a continuous fluid, as once thought, but carried by discrete particles, tiny, negatively charged entities he called corpuscles. Today, we know them as electrons. This discovery was more than a milestone in physics, it was a revelation. The electron was the first fundamental particle ever identified, the first proof that matter itself was built from smaller, indivisible components. But the idea also raised new questions. How could these charged particles fit into Maxwell's picture of continuous electromagnetic fields? Was matter itself somehow tied to these fields, perhaps even born from them? In the years that followed, scientists across Europe sought to connect the dots. If electrons were real, They must generate and respond to electromagnetic fields exactly as Maxwell's equations predicted. The boundaries between matter and energy began to blur. Some physicists proposed that all matter might, in fact, be a manifestation of the field, a localized knot of electromagnetic energy. Though the idea was too radical for its time, it hinted at something profound: the universe was not built from solid particles, but from patterns in an invisible field. Meanwhile, in laboratories from Berlin to Paris, other anomalies began to challenge the classical order. The speed of light, which Maxwell had calculated from his equations, seemed to be an unchanging constant. Yet according to Newton's laws, the speed of any moving object should depend on the observer's motion. No matter how scientists tried to reconcile the data, the results were stubborn: the speed of light remained fixed. This mystery struck at the heart of physics. If Maxwell's equations were correct, and every experiment said they were, then the very concepts of space and time might need to be reimagined. Into this storm of confusion stepped a quiet, unassuming patent clerk in Switzerland named Albert Einstein. Einstein had grown up in awe of light. As a teenager, he often imagined what it would be like to ride alongside a beam of light, moving at its speed. What would he see? How would time appear? Decades later, as a young man reading Maxwell's equations, he realized that they held the answer. The mathematics insisted that light always traveled at the same speed, no matter who observed it. The only way this could be true, Einstein realized, was if time and space themselves adjusted to preserve that constancy. In 1905, Einstein published his paper on the special theory of relativity, a work that would change the course of history. At its core lay Maxwell's legacy. Einstein's insight was that Maxwell's equations were universal. They held true for all observers, everywhere, regardless of their motion. The structure of space and time had to bend to make this possible. The speed of light, born from Maxwell's unification of electricity and magnetism, became the cosmic speed limit of the universe. In that sense, Maxwell had not only connected light, electricity, and magnetism, he had unknowingly connected energy, mass, space, and time. Einstein himself would later say that the special theory of relativity owes its origins to Maxwell's equations. The two great revolutions of modern physics, relativity and quantum theory, both sprang from the soil Maxwell had cultivated. While relativity redefined the structure of space and time, another mystery was emerging from the realm of the very small. Experiments with light and matter were revealing that energy did not flow smoothly as waves alone, but came in discrete packets, quanta. The photoelectric effect, in which light striking a metal surface could knock out electrons, could only be explained if light itself carried energy in small bundles. The idea seemed impossible. How could something described so beautifully by Maxwell's continuous waves also behave like particles? The tension between waves and particles ignited a new revolution, quantum mechanics. Yet even here, Maxwell's fingerprints remained. His field equations had introduced the concept of energy existing independently of matter, spread out in space like a living fabric. Quantum physics took that idea further, suggesting that the entire universe might be a symphony of quantized fields, each vibrating in its own frequency. The electromagnetic field became the prototype for all future field theories, from the quantum fields of electrons to the forces that bind atomic nuclei. By the early 20th century, Maxwell's unification had become the foundation of every major scientific and technological breakthrough. Engineers harnessed his equations to build power grids, design electric motors, and transmit signals across continents. Radio, radar, television, and eventually wireless communication, all were direct descendants of his vision. In laboratories and classrooms, his equations were no longer abstract. They were the blueprint of modern civilization. But Maxwell's influence went beyond utility. His work had changed how humanity thought about reality itself. Before him, science had viewed the world as a collection of mechanical parts, governed by local interactions. After him, the universe was seen as an interconnected field, alive with energy and motion. Space was no longer empty. It was a dynamic medium, filled with invisible forces shaping everything within it. This idea prepared the intellectual ground for Einstein's general theory of relativity, in which even gravity would be described not as a force, but as the curvature of spacetime itself, a concept that mirrored Maxwell's vision of fields. Through the early decades of the 20th century, physicists continued to explore the implications of this new worldview. The concept of the field became the unifying principle of physics, linking electromagnetism, relativity, and quantum mechanics. Every new discovery seemed to trace its lineage back to Maxwell's equations. When physicists later developed the Standard Model, the grand theory describing all known fundamental forces except gravity, they once again relied on Maxwell's mathematical structure as their foundation. His equations had become the universal grammar of the physical universe. Yet, behind this monumental legacy was a man who never sought grandeur. Maxwell had been a quiet soul, gentle and humorous, often reciting poetry or discussing philosophy between his mathematical explorations. He once said, "Thoroughly conscious ignorance is the prelude to every real advance in knowledge." It was that humility, his willingness to question, to imagine, and to see beyond the obvious, that made his genius so rare. Today it is easy to take for granted the world he made possible. When we flip a light switch, charge a phone, or connect to Wi-Fi, we are surrounded by electromagnetic phenomena that obey his laws perfectly. Every flicker of a screen, every hum of a motor, every signal beamed from a satellite is an echo of his work. The universe that Maxwell revealed, vibrant, unified, and alive with energy, is now the world we live in. But there is something deeper still. Maxwell's unification did not merely advance physics, it revealed a philosophical truth about nature. That simplicity lies at the heart of complexity, that beauty is a sign of truth. His equations, when written out in their elegant form, contain within them the seeds of everything from the rainbow in the sky to the signals of deep space. They are not only mathematical expressions but works of art, symphonies of logic composed by a mind attuned to both precision and wonder. In classrooms across the globe, his name is mentioned alongside Newton and Einstein, but unlike them, Maxwell's fame has remained quieter, less adorned with myth. Yet among scientists, there is no doubt his work marks the true turning point between classical and modern physics. Newton revealed motion and gravity, Maxwell revealed energy and light. The world before him was mechanical, the world after him was electromagnetic. As the 19th century gave way to the 20th, the torch of discovery passed from Maxwell's hands to those of Planck, Einstein, Bohr, and Heisenberg. They would carry his legacy into new realms: quantum theory, relativity, and the atomic age. But the rhythm beneath it all, the heartbeat of the field, remained Maxwell's. Every discovery since has been a variation on his theme, an elaboration of the harmony he first perceived in the interplay of electricity and magnetism. He had once written that the goal of science was not merely to catalog facts but to perceive the hidden connections among them. In that sense, Maxwell achieved something eternal. He did not simply describe a force, he uncovered a principle of unity that reaches across all of nature. The light that shines from a distant star, the magnetic pull of the earth, the spark that leaps from a fingertip, all are threads in the same cosmic web he revealed. As his ideas spread through generations, they inspired not only physicists but artists, philosophers, and dreamers who saw in his equations a glimpse of the universal order. Maxwell had transformed invisible forces into visible knowledge, showing that the universe speaks in the language of mathematics, and that when we learn to read it, we discover beauty as profound as any poem or song. His work marked the end of one age and the beginning of another. The mechanical clockwork of Newton had given way to a universe of light, energy, and motion, a universe bound together by the symmetry of Maxwell's laws. The dawn of modern physics had arrived, and with it, a new understanding of our place in the cosmos. As the new century unfolded, the echoes of Maxwell's vision grew louder. What had begun as a set of equations scribbled in a notebook now pulsed through laboratories, factories, and even the heavens. The invisible waves he described filled the Earth's atmosphere, whispering through telegraph lines, resonating in the first radio transmissions, and soon crossing oceans. It was as if the world itself had begun to hum to the rhythm of his mathematics. When Einstein published his special theory of relativity, the scientific community was stunned. But within that shock, there was a quiet recognition. The cornerstone of his argument was not something new, it was Maxwell's light. Einstein had built an entirely new concept of the universe around the constancy of electromagnetic radiation. The equations of Maxwell, once thought to apply only to magnets and coils of wire, were now dictating the nature of space and time themselves. In his own reflections years later, Einstein admitted that he had merely followed the trail Maxwell left behind. Before Maxwell, he said, physical reality was thought of as consisting of particles with forces acting between them. Since Maxwell, we have had the concept of physical reality in the form of fields. That transformation was nothing less than the birth of the modern worldview. But the revolution did not stop there. If relativity was one child of Maxwell's work, quantum theory was its other. The idea that energy existed in discrete quanta seemed, at first glance, to contradict the smooth, continuous fields Maxwell had described, yet the tension between the two ideas only deepened scientists' understanding of nature. Light, it turned out, could be both a wave and a particle, both the continuous field and the discrete quantum. It was as if Maxwell's invisible waves had folded upon themselves, revealing a dual nature hidden within the fabric of reality. The early pioneers of quantum mechanics, Planck, Bohr, Schrödinger, and Heisenberg, grappled with this paradox. They realized that fields were not just mathematical abstractions, but living entities that fluctuated, vibrated, and exchanged energy in mysterious, quantized ways. The field had become the stage on which all physical phenomena played out, and Maxwell's work was its script. Then came the dawn of the atomic age. When scientists split the atom, they released forces far greater than anyone had imagined. Yet even in the terrifying brilliance of nuclear energy, Maxwell's influence could be felt. The electromagnetic force, one of the four fundamental interactions of nature, remained the key to understanding how matter behaved at every scale, from the orbit of electrons to the reactions in the heart of stars. The mid-20th century brought an explosion of technological progress that seemed to vindicate every line of Maxwell's equations. Radio and television networks knitted the planet together with electromagnetic signals. Radar-guided airplanes through storms and submarines beneath the sea, lasers, fiber optics, and satellite communications all drew their lifeblood from the same unified principles. Every spark of innovation traced its lineage back to the Scottish physicist who had glimpsed unity in diversity. Meanwhile, theoretical physics entered a new golden age. Scientists sought to expand Maxwell's framework, combining electromagnetism with the quantum realm. This effort gave rise to quantum electrodynamics QED, the most precise and successful theory ever devised. In the 1940s, physicists such as Richard Feynman, Julian Schwinger, and Sin Itaro Tamanaga reformulated Maxwell's equations in quantum language, describing how light and matter interact at the smallest scales. Their work confirmed that Maxwell's vision could survive the leap from the macroscopic to the microscopic, from the human world to the subatomic. QD revealed that empty space is not truly empty, but seethes with virtual particles, constantly emerging and annihilating in a restless dance. The electromagnetic field fills all of space, its fluctuations shaping the very structure of matter. This concept echoed Maxwell's intuition more than a century earlier, that space is alive with energy, that fields are the true substance of reality. By mid-century, physicists had succeeded in uniting the electromagnetic and weak nuclear forces into a single theoretical framework, the electrowake theory. Once again, Maxwell's equations provided the foundation. His field concept had grown beyond electromagnetism, it had become a universal language. Just as he had unified electricity and magnetism, modern theorists now sought to unify all the forces of nature. The ultimate dream, the so-called theory of everything, is nothing more than the continuation of Maxwell's quest for unity. Even the exploration of space carried Maxwell's signature. Every spacecraft that left Earth, every telescope that peered into the cosmos, relied on electromagnetic communication, on the manipulation of light and radio waves. When the Voyager probes sent back images from the edge of the solar system, the signals traveled as faint electromagnetic pulses across billions of kilometers, a direct testament to Maxwell's discovery that light and radio are one and the same. And yet, beyond the technology, beyond the equations, lies a more profound human story. Maxwell's legacy is not only scientific but spiritual. He showed that beneath the apparent chaos of nature lies order, beneath the diversity of phenomena lies unity. The universe, he proved, is not a random collection of disconnected events but a single, coherent whole governed by simple, elegant laws. In a world fractured by human divisions, that idea remains deeply inspiring. The same laws that govern the motion of a planet also describe the flicker of a candle, the color of a sunset, and the whisper of a radio wave. Maxwell's insight reminds us that all things are connected through the same cosmic fabric. The 21st century continues to uncover new layers of this truth. Quantum field theory, string theory, and modern cosmology all draw their heritage from Maxwell's idea that fields, not particles, are fundamental. According to these theories, the universe itself may be a vibrating network of fields, its particles nothing more than localized excitations within a universal energy sea. In other words, the world is made not of things but of relationships, patterns of energy and information. This was precisely the intuition that guided Maxwell a century and a half ago. Consider for a moment how deeply this has transformed our lives. Without Maxwell's equations, there would be no electricity powering our homes, no computers, no smartphones, no internet, no medical imaging, no radar or GPS. The rhythm of modern civilization, the pulse of every city on Earth, is driven by the dance of electrons he described. When you switch on a light, you are not merely performing a mundane act, you are invoking the same principles that connect distant galaxies through their starlight. In the digital age, the human world has become an electromagnetic web. Every message, every call, every stream of data is carried by waves that Maxwell predicted. The boundaries between science and daily life have blurred so completely that his ideas now form the invisible infrastructure of existence itself. Yet, astonishingly, most people who depend on his work each day may never have heard his name. Among physicists, however, his legacy glows brightly. They still marvel at the simplicity of the four equations that describe the electromagnetic field. Written on a single line, they encode the behavior of light, radio, electricity, and magnetism, everything from the aurora in the night sky to the circuits in a supercomputer. When students first encounter them, they often feel a sense of awe. How can so much of the universe be contained in so few symbols? That sense of beauty, of hidden order, is the essence of Maxwell's gift. In the great narrative of science, his contribution marks a turning point comparable to Newton's and Einstein's. Newton revealed the law of gravitation, Maxwell revealed the law of radiation. Einstein curved space and time to preserve the speed of light, while Maxwell first gave light its meaning. It is no exaggeration to say that without Maxwell, neither relativity nor quantum mechanics could have existed in their present form. The deeper one looks, the more one realizes that Maxwell's equations are not just tools. They are expressions of a profound symmetry in nature. They show that electric and magnetic phenomena are mirror images, intertwined aspects of a single entity. This symmetry echoes through every branch of modern physics, from gauge theory to the geometry of spacetime. It is as if the universe itself is written in the dialect of symmetry, and Maxwell was the first to hear its grammar. As science advances into realms Maxwell could never have imagined, nanotechnology, quantum computing, gravitational waves, his framework continues to provide guidance. The manipulation of electromagnetic fields at atomic scales lies at the heart of quantum processors, The detection of gravitational waves relies on laser interferometry, a direct descendant of his optical theories. Even the search for dark matter and dark energy, the mysterious components that make up most of the cosmos, builds upon his concept of fields permeating space. The continuity between his 19th century insights and 21st century frontiers is astonishing. Maxwell's work has become timeless because it touches something universal, the relationship between simplicity and truth. The more deeply scientists probe into the universe, the more they encounter patterns that echo his equations. It is as if his mathematics were not an invention but a discovery of something woven into reality itself. And yet, beyond the laboratories and the equations, there remains a quieter, more personal legacy, the legacy of a man devoted not to fame or fortune, but to understanding. Those who knew Maxwell spoke of his kindness, his humor, and his unwavering curiosity. He often played music for his students, comparing the harmony of notes to the harmony of natural laws. To him, science was not merely an occupation, it was an act of worship, a way to glimpse the divine order behind the veil of appearances. In the final years of his life, as illness weakened his body, Maxwell remained serene. He continued to teach, to write, and to reflect on the beauty of the universe. When asked what drove his work, he answered simply that he wished to know the thoughts of God concerning the electric and magnetic fields. To many, that humility is what makes his genius most extraordinary. Today, when we look up at the stars or down into the circuits of our devices, we are seeing Maxwell's vision come alive. The universe he revealed is radiant, interconnected, and dynamic, a cosmos of waves and energy, of patterns and possibilities. His unification of electricity and magnetism became the blueprint for all future unifications, the first step toward understanding the oneness of nature. Every new generation of scientists stands on his shoulders. Every equation that seeks to unite the forces of nature traces its ancestry to the field concept he birthed, and every spark of innovation that lights the world is, in a sense, a continuation of his dream. In the end, Maxwell's true legacy is not only in what he discovered, but in how he changed the way humanity thinks. He taught us to look beyond the visible, to imagine the invisible structures that underlie reality. He showed that beauty and truth are not separate pursuits, but reflections of the same cosmic order. So when the hum of electricity fills the night, when the glow of a screen connects distant minds, when the radio waves ripple through the air carrying voices across the globe, we are living inside Maxwell's universe. It is a universe where energy and matter, light and life, are intertwined, where the simple elegance of an equation can illuminate the mysteries of existence. From the quiet countryside of Scotland to the laboratories of the future, his influence endures, unchanged, unbroken, and eternal. Maxwell's legacy is the story of humanity's awakening to the hidden harmony of creation, the realization that the same forces that light the stars also flow through our hands. His equations are not just scientific symbols, they are the music of the cosmos, written in the universal language of mathematics. And as long as there are minds to question, eyes to wonder, and hearts to seek understanding, the song that Maxwell began will never fade. It will continue to echo through time, an endless symphony of light. In the mid-19th century, when science was still sorting out the boundaries between the seen and the unseen, James Clerk Maxwell made a prediction so daring that even his peers struggled to believe it. Through the elegant mathematics of his field equations, he had found that disturbances in the electromagnetic field would move through empty space at a fixed speed, a speed that matched, with astonishing precision, the measured speed of light. From this coincidence he drew a conclusion that seemed almost mystical for its time. Light itself was an electromagnetic wave. The flicker of a candle, the color of the dawn, the flash of a thunderbolt, all were vibrations of invisible electric and magnetic fields sweeping through the void. At first, the idea was hard to grasp. Many scientists believed that waves required a medium, some substance to carry them, and so they imagined a mysterious, luminiferous ether filling all of space. Maxwell's insight hinted that no such substance was necessary. The fields themselves were real enough to sustain motion. This was a radical leap, to treat emptiness as alive with structure and energy. In the quiet of his study, Maxwell realized that nature's most beautiful phenomena could be described by a few lines of mathematics, equations that not only united electricity and magnetism, but revealed light as their offspring. For the first time, the barriers between phenomena that humans had always seen as distinct began to dissolve. A magnet moving near a wire could create an electric current. An electric spark could generate light. Light could be bent by fields. Color itself was a measure of frequency. Maxwell's equations did not just explain one puzzle. They reimagined the entire relationship between matter and energy. The spectrum of light, from radio waves to X-rays, was born from this realization, though it would take decades before technology caught up enough to confirm it. His vision reached far beyond the laboratories of his century into a future filled with antennas, transmitters, and glowing screens. When scientists like Heinrich Hertz later produced electromagnetic waves in the laboratory and measured their speed, they confirmed what Maxwell had only foreseen with pen and paper. Each experiment was a whisper from the universe agreeing with his prediction. It became clear that light was just one small portion of a vast, continuous sea of electromagnetic radiation, invisible waves surrounding the Earth and stretching across the cosmos. From that moment, humanity's understanding of light transformed. It was no longer a mystical illumination, but a measurable, physical phenomenon that could be shaped, directed, and harnessed. This discovery reshaped every field it touched. Astronomers learned to see the universe not just with optical telescopes, but with radio and infrared detectors, revealing worlds hidden in darkness. Engineers learned to control electromagnetic waves to send messages across oceans and into space. Artists, too, found inspiration in Maxwell's synthesis, in the knowledge that color and light were part of the same grand harmony of vibration. What had once been a purely scientific theory became a bridge between disciplines, connecting imagination with technology, poetry with precision. Maxwell's realization that light was an electromagnetic wave did more than explain the glow of the sun. It revealed a fundamental truth about the universe. It showed that nature's forces are not separate kingdoms, but interwoven aspects of one grand tapestry. In every beam of light, in every signal that crosses the sky, in every electrical pulse that powers human civilization, his insight continues to shine. More than a century after his death, the world still moves to the rhythm he uncovered, the invisible dance of electricity and magnetism that we simply call light. In his lifetime, James Clerk Maxwell stood in the shadow of giants yet unseen, his brilliance often overlooked by the scientific community of his day. While he had uncovered one of the deepest unifications in the history of science, the marriage of electricity, magnetism, and light, his discoveries were too advanced for many of his contemporaries to fully grasp. The world was still guided by the simplicity of Newtonian mechanics, where forces acted at a distance and particles followed predictable paths. Maxwell's equations, filled with vectors, fields, and invisible waves, felt abstract and unfamiliar to an age that preferred tangible machinery and direct observation. His genius had leapt ahead of his time, and the recognition he deserved came only long after his voice had fallen silent. In the universities of the 1860s and 1870s, Maxwell's theories were treated with a mixture of respect and uncertainty. Some admired the beauty of his mathematics but doubted its physical meaning. Others dismissed his electromagnetic field as a convenient fiction, a way to describe effects rather than reality itself. To the practical engineers of the era, his equations seemed too theoretical, too distant from the problems of building engines or telegraphs. The Industrial Revolution was roaring. Yet Maxwell's revolution of ideas moved quietly, carried only in academic papers and the minds of a few open thinkers. Even Maxwell himself seemed indifferent to fame. He was a man of humility and humor, content to teach, to experiment, and to explore. He published his treatise on electricity and magnetism in 1873. a monumental work that distilled the essence of his theory into a form the world could study. But the book's complexity meant that only a handful of readers could appreciate its depth. It contained the future of physics hidden in its pages, waiting for someone with vision to see it clearly. For many years, that future remained unread. It wasn't until after Maxwell's death in 1879 that the seeds he had planted began to bloom. Experimentalists like Heinrich Hertz would go on to confirm his predictions by generating electromagnetic waves in the laboratory, proving that invisible fields truly existed and moved through space just as Maxwell described. The delayed recognition revealed how far ahead his mind had been, how he had glimpsed truths that even the instruments of his time could not yet reveal. Slowly, the scientific world began to awaken to the realization that Maxwell's work was not merely a theory, but a description of reality itself. In those early years of neglect, one can sense the loneliness of a visionary. He lived in a world where his discoveries were seen as curiosities rather than cornerstones, where his genius seemed out of step with the rhythm of his age. Yet Maxwell never expressed bitterness. He once wrote that, "The true aim of science is to find the harmony which exists between the laws of nature and the laws of reason." To him, discovery was its own reward. He was not seeking applause but understanding, not fame but truth. His quiet perseverance became a model of scientific devotion, the belief that one must serve knowledge even if recognition never arrives. When the new century dawned, and the works of Einstein, Planck, and the quantum pioneers began reshaping physics, Maxwell's name re-emerged like a buried treasure rediscovered. Einstein himself would later say that the foundation of his theory of relativity rested entirely on Maxwell's equations. What had once been dismissed as abstract mathematics became the language of the universe. The physicist who had struggled for attention in life became, in death, one of the most revered figures in all of science. Maxwell's struggle for recognition reminds us that the world often takes time to understand the greatest minds. His equations were too profound to be instantly appreciated. They demanded a new way of thinking about nature itself. But true genius does not fade with neglect. It waits, and when the world finally catches up, the brilliance shines even brighter. Maxwell's story is the story of patience, vision, and faith in truth. It is a testament that even in the silence of obscurity, the light of discovery never stops burning. When the 20th century opened its doors to new ideas, the name of James Clerk Maxwell began to rise from quiet respect to reverent awe. His equations, once confined to textbooks and the minds of a few mathematicians, became the foundation upon which modern physics was built. The young Albert Einstein, still a patent clerk in Switzerland, found in Maxwell's work the spark that would ignite his own imagination. As Einstein studied the strange symmetry of the electromagnetic equations, he noticed something that defied common sense. No matter how fast one moved, the speed of light remained constant. That single observation, hidden in the mathematics of Maxwell, would lead Einstein to one of the greatest revolutions in scientific history: the theory of relativity. Einstein often said that he stood on the shoulders of Maxwell. Without those equations, relativity might never have been born. Maxwell's work suggested that space and time were not separate entities, but woven together by the behavior of light and fields. In Einstein's hands, this became the principle that space and time themselves could bend, stretch, and warp. The essence of modern physics. It was a chain of inspiration that stretched across generations, from the quiet Scottish countryside where Maxwell first imagined invisible waves, to the modern world of quantum fields and curved spacetime. But Einstein was not the only one touched by Maxwell's legacy. The early quantum theorists, too, drew deeply from his well of insight. Max Planck, in his studies of blackbody radiation, was guided by the understanding of electromagnetic energy that Maxwell had first unified. Niels Bohr's model of the atom, with electrons orbiting around a nucleus and emitting light in discrete packets, was a direct descendant of Maxwell's view of light as a wave in motion. Even Werner Heisenberg and Erwin Schrödinger, in their explorations of uncertainty and wave mechanics, worked in a world already shaped by Maxwell's concept of fields that vibrate through space. Through these connections, Maxwell became the unseen architect of the quantum age. His equations described the large-scale behavior of electromagnetic fields, but their structure hinted at a deeper truth, that nature itself was built on vibrations and frequencies, patterns of energy rather than solid matter. Quantum mechanics would later reveal that everything in the universe, from electrons to galaxies, behaves as both particle and wave. It was as if Maxwell's waves had expanded to encompass all of existence. In every corner of modern science, traces of his genius can be found. The communication systems that link continents, the medical imaging that peers inside the human body, the radio telescopes that listen to the whispers of distant galaxies, all rely on the laws Maxwell discovered. His work did not just transform physics, it transformed civilization. Each new generation of scientists found his equations waiting, perfectly balanced, perfectly true, as though they had always been part of nature, waiting only to be discovered. And yet, what makes Maxwell's influence most extraordinary is not just its scientific scope, but its philosophical depth. His equations did not merely describe phenomena, they revealed a universe bound by unity and symmetry. The idea that light, electricity, and magnetism were expressions of the same underlying force gave humanity its first glimpse of the interconnectedness of nature. Later physicists would follow this thread toward even greater unifications. The electroic theory, the strong force, and the dream of a single theory of everything. Each of these efforts is a continuation of the path Maxwell began. Einstein once remarked that if the laws of physics could be expressed as music, Maxwell's equations would be the opening symphony. Simple, elegant, and eternal. Their melody still resonates through every scientific discovery, from the bending of light around massive stars to the quantum entanglement that defies classical understanding. In uniting electricity, magnetism, and light, Maxwell unknowingly opened the door to the age of relativity and the quantum world beyond. His influence was not confined to laboratories or equations, it became the invisible rhythm of human progress. Every radio signal, every beam of light, every pulse of energy that carries information across the planet is part of Maxwell's living legacy. The discoveries of Einstein and the quantum pioneers did not replace his vision, they expanded it. Each breakthrough, no matter how revolutionary, still carries the echo of Maxwell's insight, that nature is not a collection of separate parts, but a seamless web of relationships, moving to a harmony that mathematics alone can describe. In the end, Maxwell's gift to Einstein, to Planck, to all who came after, was more than a set of equations. It was a way of seeing. He taught humanity that behind the visible lies an unseen structure, elegant and unified, where light binds the cosmos together. His influence on modern physics is immeasurable, his spirit woven into every discovery that has followed. From relativity to quantum mechanics, from radio waves to the stars, Maxwell's vision continues to illuminate the path of science, a light that has never dimmed. As the decades passed and science advanced into realms Maxwell could scarcely have imagined, his name grew from the pages of dusty journals to the heart of modern civilization. The invisible waves he once predicted now fill the air around us, carrying voices, images, and data across continents in the blink of an eye. Each time a signal travels from one device to another, it retraces the patterns he discovered long ago in the quiet solitude of his study. The world that Maxwell helped to create is one where light and information flow endlessly, shaping the way humans think, connect, and explore. His equations became not just the language of physics, but the foundation of the technological age. When we look around at the modern world, at satellites orbiting the Earth, at the glowing screens that define daily life, at the wireless networks that connect billions, we are seeing the living legacy of James Clerk Maxwell. His discoveries turned invisible forces into the framework of human progress. Radio, television, radar, microwaves, mobile communication, and even the Internet owe their existence to his understanding of electromagnetic waves. Every photograph transmitted from Mars, every call made across oceans, every heartbeat recorded in a hospital scanner, all of it carries Maxwell's invisible signature. The electric pulse of civilization beats to the rhythm of his equations. Yet, despite the enormity of his contributions, Maxwell himself remained a man of remarkable humility. He never sought fame or recognition, and in his lifetime, few understood the magnitude of what he had achieved. To many, he was a mathematician lost in abstraction, a mind too far ahead of its time. But time itself would vindicate him. As science moved forward, as experiment after experiment confirmed his predictions, Maxwell's vision was revealed as one of the purest glimpses humanity has ever had into the mind of nature. In the years following his death, physicists began to realize that Maxwell's equations were not just a theory of electromagnetism. They were a statement about the deep symmetry of the universe. They revealed that light was an electromagnetic wave, that the speed of light was fixed, and that energy and motion were bound by mathematical harmony. This realization became the seed from which all of modern physics would grow, the technology that powers cities, explores planets, and peers into the quantum realm all trace their roots to the same source, the unity that Maxwell discovered between electricity, magnetism, and light. Today, his work stands as a timeless bridge between the physical and the philosophical. He showed that unseen forces could be described by elegant mathematics, and in doing so, he gave humanity a way to understand the invisible structure of reality. His legacy is not only in equations but in the way he changed the human view of the universe. Before Maxwell, light and electricity were separate mysteries. After him, they became parts of one grand, interconnected whole. This vision reshaped not just physics, but the human imagination itself. Modern scientists continue to walk in his footsteps. Whether it's in the search for unified field theories, or the exploration of quantum fields that govern the universe, Maxwell's spirit guides every discovery. The dream of uniting all the forces of nature, gravity, electromagnetism, and the quantum realm, is a continuation of the journey he began. His equations still whisper their secrets to those who listen, inviting new generations to see the world not as chaos but as a tapestry woven from symmetry, balance, and light. In the end, James Clerk Maxwell's story is more than the tale of a scientist. It is the story of how one mind, driven by curiosity and faith in the beauty of truth, changed the world forever. His discoveries bridged the gap between the seen and the unseen, between knowledge and wonder. Through his work, humanity gained not just control over energy and waves, but a deeper understanding of the unity that binds the cosmos together. His light continues to shine, not only through the devices and technologies that shape the modern world, but in the eternal quest of the human spirit to understand the mysteries of creation. Maxwell's genius endures, not as a memory of the past, but as a force still alive in every spark of innovation, every beam of light, and every question that begins with the same wonder he once felt beneath the vast Scottish sky.